Hello! This is a deep dive into GPU text rendering. My name is Elijah Stone. You may know me from... well, never mind that. Let's just get right into it. GPUs are pretty neat. I mean, sure, nobody wants to code for them. It's a complete pain. But when you compare raw flops and memory bandwidth, GPUs come out probably 50 to 200 times faster than CPUs. Even an integrated card, just a little chip on the back of your CPU, could be 5, 10, 20 times faster. I think most people would be pretty happy to get even a 50% improvement in performance. Of course, nothing is free. The trick is that you have to formulate your problem in a way that the GPU can understand. In some cases, this is completely easy, bordering on trivial. Like, say, rasterizing polygons. It's like hardware-assisted memcopy. Nothing to it. Some things are really hard. Like, there's this matrix transposition library I've been trying to hunt down for a while now. It works by rendering the matrix into 4 dimensions and then transposing 2 of them at once. Or this one guy figured out how to make a compiler that runs in parallel on the GPU, and he wrote this entire PhD thesis about it. Today I want to talk about something that sits sort of in the middle, text rendering. What we want to do is to use the GPU to render text. So the program that I wrote to deliver this presentation runs on the GPU, and it seems to be rendering text right now, so I guess we're done. Right. This text is bitmapped. Now, I know some people like them, but personally, I'm not really a fan. I like resolution independence and anti-aliasing, so I want to render text that has curves in it. How do we do that? We're going to need some kind of representation, a way of talking about curves in a way that's not reliant on any particular grid, and the most basic primitive of our representation, which is what most fonts these days use, is called a Bezier curve. A Bezier curve is defined in terms of 3 points, which are called control points. By the way, order is important. And we can sample the curve that we define here in terms of an interpolant between 0 and 1. Let's say that we wanted to use 3/4. We would start by going 3/4 of the way from point 0 to point 1, 3/4 of the way from point 1 to point 2, and then 3/4 of the way from the first intermediate point to the second intermediate point. We can do this for anything else, like say 1/4, or 1/2, or any other number between 0 and 1. And the idea is that if we did this for all real numbers between 0 and 1, we would eventually get all of the points on this clearly curve-shaped thing. We're programmers. We don't want to see pictures, we don't want to see what things look like. So here's one way you might render this into code. A point is a structure which has x and y components. A curve is a structure which has 3 of those doodads. It has a method for sampling the x component of a point some distance along this curve. We have a contract that the distance must be between 0 and 1, because that's what we said. We can use interpolants between 0 and 1, but not outside of that range. This is the actual definition of that method. Don't worry too much about this, we're going to come back to it. We have the exact same method for y, though. You know, it seems like we could just have a single method for sampling a point, and maybe like operator overloading or whatever, but we don't. We have 2 separate methods, and we force the caller to call both of them using the same interpolant and construct a point from the results, which seems redundant, but it turns out to be really important. Now again, we are going to come back to this. The details here are not super important. If you are interested and want to pause the video and chew on this definition for a minute, maybe look up the definition of lerp if you're unfamiliar with it, feel free, but if not, no big deal. Alright, problem. We've come up with a representation for curves, in particular deformed line segments. Line segments don't have width, and we want to render glyphs that have width. How do we solve this? We just trace the outline of a glyph. So Here's the outline of the glyph for the letter O. Every set of 3 points, 2 blue, 1 red, forms a Bezier curve. So the blue points are all shared between 2 curves. And then we just say that, every point that's inside this curve is part of the shape. But we have a problem. Computers need precise definitions. And we don't have a precise definition of what it means to be inside of this outline. For instance, we might say, yep, everything is inside the outline, so we paint it green. But obviously that's not what we want. We want this. For that matter, we might say we painted this whole infinite expanse white and left the green parts untouched. But again, that's obviously not what we want. So what definition do we use? Before continuing, it's worth taking a moment to think with an eye towards eventually actually rendering something on a glyph of pixels, what that algorithm would look like. And in particular, very broadly, there are 2 approaches that we could take, which I'm going to call generative and predicative. The first approach, the generative approach, is where you look at the whole shape holistically, and you generate a sequence of all the points that are inside, and you visit all those points, and you paint them. Sounds good? The predicative approach, the other approach, is that you visit all of the points on your canvas, every pixel, and you ask, is this pixel inside or out? And if it's inside, you paint it. If it's not, you move on to the next one. Now, as programmers, we're trained to be lazy and do as little work as possible, so we naturally gravitate to the generative approach. I mean, why do work you don't have to? Why visit pixels you don't have to? And this is actually what you do when you render on the CPU. However, the advantage of the GPU is that it's massively parallel, and the predicative approach, where you visit everything, is embarrassingly parallel because there are no interdependencies between the points. So when we render on the GPU, we can actually visit all of the points in parallel and paint or not paint all of the points, all of the pixels in parallel. And this is nice because this is actually more mathematically correct. It's closer to the mathematical definition, because mathematically it has to be defined for arbitrary points, not just pixels on a particular grid. Anyway, getting back down to business. Remember when I said that the order of these points was important? Here I've added arrows showing for each one of these curves the direction that it's going. So here I have 1, 2, 3 points in one Bezier curve. They have to go in this order, 1, 2, 3, not in the opposite order. And if you notice, all of the curves in the outer contour go clockwise, and all of the curves in the inner contour go counterclockwise. And this is what makes it so that we don't paint the part in the center, but we do paint the disk around it. I'm sorry, the strip around it. So let's look at an example of how we would run this predicate for a single point. Let's say we're looking at this point, magenta, and we're trying to decide whether we should paint it or not. We start by initializing a counter to 0, and then we cast out a ray from this point towards infinity. We can cast it in any direction, we get to decide, and we should get the same answer no matter what. So for simplicity, let's just cast it up. Nothing happened. The final value of our counter is 0, so we don't paint this point. Here's another example. We're trying to decide whether we should paint this point. We initialize our counter with 0, we cast a ray upwards, and we hit an intersection. The curve that we intersected with is going right. Since it's going right, we add 1 to our counter. If it were going left, we would subtract 1. We keep going, nothing else happens. The final value of our counter is 1, so we do paint this point. 2 more. This point, we initialize our counter with 0, we cast out a ray. We hit a leftwards moving curve. It's moving left at the point where we intersect with it, so we subtract 1, keep going. This time the curve we intersect is going right, so we increment our curve, keep going, and nothing else happens. The final value is 0, so we don't paint anything in this center part. Finally, we paint this. We go upwards, we hit a curve, and in this case it's going left, so we decrement our counter, keep going, we hit another curve on the same contour, but because this time we're leaving it, it's moving right with respect to our array. So we increment our counter and keep going. Nothing else happens, so we don't paint at this point. The intuition for this algorithm should be fairly straightforward, because if you're inside of a shape, at some point you will leave it, and that will change the value of your counter. If you're not inside of a shape, maybe you miss it completely with your array, maybe your array enters it and you change the value of your counter, but the array will also have to leave the shape at some point, and when it leaves it, that'll cancel out the change to your counter that happened when you entered the shape. Here's how we would express this with code. Initialize a counter, create a array going from the point that we're trying to paint towards infinity in the y direction. We iterate over all the curves in the outline for the glyph that we're trying to render. We calculate all the intersections between that curve and this array. If the intersection goes right, we increment our counter, otherwise we decrement it. Finally, if the final value of the counter was non-zero, we paint our point. This should be fairly clear, fairly straightforward, except for one wrinkle. How do we calculate intersections? Something to notice is that we cast our ray towards infinity in the y direction, but the ray does not move at all in the x direction. All points on the ray have the same x-coordinate, which is the same as the x-coordinate of the point that we're trying to paint. What that means is that in order to find collisions or intersections, all we have to do is find points on the curve whose x-component is the same as that of our point. Here's the function for sampling the x-component of the curve again, and again, not worrying about this definition, lerp is a fairly simple algebraic function, but if we expand those calls, we get this. And this is a quadratic function in terms of t, which means that we can invert it if we know the point values, which we do. So to find the t values, all we have to do is just run the quadratic formula, which looks like this. Fairly straightforward. Problem, though. It seems like this function always gives us two results, and sometimes we have two collisions or two intersections with a curve, but sometimes we just have one intersection or none. This function returns two values, two potential results, two potential intersections, but sometimes one or both of them is bogus. So we have to know when to throw out these results. If the result is nan, we throw it out. That means that the t-value was complex. We don't care about complex numbers. We also throw out results which are not in the 0 to 1 range, because we said Bezier curves can only be sampled using interpolants between 0 and 1. A result which is outside of that range means if this is our curve and this is our ray we're checking for intersections with. A result outside of the 0 to 1 range means if we extended this curve beyond its normal limit, we would have an intersection, but we don't. Finally, we have to sample the y component of that point, and we have to make sure that it's above the y-coordinate of our point. And here's an example of where this would come up. In this case, we have a point on the curve whose x-component coincides with the x-component of our point, but the curve dips below the point that we're trying to paint, so it doesn't actually intersect with the array. Alright, so now we have identified our intersections. The last thing we need to do is figure out whether an intersection goes right or left. How do we do that? Calculus rarely beats good old-fashioned brute force. We just sample the x-component of the points on the curve immediately before and immediately after this result point, and we see if it seems to be increasing or decreasing at that point. Ta-da! Alright, let's make it even better. I said that brute force wins, but there are actually some problems with this brute force approach. Number one, how do we choose our epsilon value? Epsilon is just means a small number, but how do we choose it? Presumably you'd want to do it heuristically, possibly based on how much floating point precision you have, maybe also based on size, but it's just, I don't know, it's kind of difficult to do. Another problem is you can have rounding errors in this sample x function, which can lead to artifacts. I mean, in general, the more computation you do on floating point numbers, the more errors you're going to end up with. Additionally, it can reduce performance to do this sampling again. I mean, I think that pretty much probably doubles the number of calculations you have to do for each pixel that you try to paint. So we want to avoid doing work, we want to avoid imprecision. What can we do? Let's look at the control points, because the control points are given to us, so you can't get anything that's higher precision, and you don't have to do any work to get them, compared with points on the curve, which you have to do computation in order to get those. Now, just knowing the values of the control points doesn't tell you whether you have an intersection or which direction it goes, but it tells you something. So here's a point I'm trying to paint, here's a ray going upward, here's a Bezier curve. All 3 points on this Bezier curve are to the left of the point that we're trying to render, and that means that we can't possibly have any intersections with this curve. Let's look at some more examples. Here we have 2 points to the left of the point that we're trying to render, and 1 point to the right. Here we have another example of the same archetype. 2 points to the left, 1 point to the right. So just knowing that there are 2 points to the left and 1 point to the right doesn't tell us whether there's an intersection. But if there is an intersection, then we know that it has to always go from the left to the right. Last example. If we have 1 point to the left of the point we're trying to render, 1 control point to the right, and then 1 control point to the left again, we might not have any intersections. We might have 2 intersections. We might only have 1 intersection. But if there are 2 intersections, the first one will go right, and the second one will go left. If there is only 1 intersection, it will have to go to the right. In general, we can say that the first intersection, if there is a first intersection, will have to be from left to right, and the second intersection, if there is a second intersection, will have to go from right to left. In total, we have 3 points, and we can classify each point as being either to the left or to the right of the point we're trying to render. That means that we have 8 total classifications of each curve, and it turns out that just knowing the classification of a curve will always tell us which direction an intersection goes in, if there is an intersection. So we still have to run the quadratic formula to figure out which intersections there are, but having done that, we don't have to rerun the sampling function multiple times in order to figure out which directions those intersections go. And that's font rendering. You know how sometimes people talk about self-hosting compilers, a compiler that can compile its own source code. What I have here is the less impressive version of that. This is the shader that can render its own source code. So we start off, we have uniforms. These are global variables. First thing is window dimensions, and then curves. Curves are the actual font data for all the glyphs in our font. We have this kind of opaque type sampler to the rect. It's just a float buffer, like pretty much everything else on the GPU. Then we have invariables, and these are like our parameters. We have curve start and length. This tells us where to look in the font data for the curves that actually correspond to the glyph that we're trying to render, because we only render 1 glyph at a time. Location and bound, this tells us where on the screen we're drawing the glyph, and that's actually, I'm not actually doing that right now, you shouldn't need that. And then we have what color we want to paint the glyph. Finally, we have our return value, or out variable, which is the color. And this will be transparent if we didn't paint anything, or it will be the color if we did paint something. We have this sampling function, same as before, we saw this already. This time it's just in GLSL, which is a language we use to run on the GPU instead of D. Then we have this wind delta function, which is the real workhorse. Pass in a curve, and it tells you if you had any intersections with that curve, what effect did that have on your counter? And the formal name for this counter mathematical name is winding number, so the function name is winding delta. We have our two result values, two potential result values from the quadratic equation, and we have for each of those results whether it's valid. Here this is, again, I'm not doing this really correctly, but it works. The point here is that we have location, which is a vector that is the location of the point that we're trying to render. Here we calculate the coefficients of our quadratic equation. We solve it, setting our two potential result values and our two validity values. This determinant greater than or equal to 0 is basically a more direct way of checking if the result is nan. This is an edge case, not super important. We do need to make sure that the curve didn't go below the point and miss the ray. In this case I'm using less than, not greater than, because I'm using a flipped coordinate space where y is up, but it's the same idea, same principle. However, we don't actually have to check that our results are between 0 and 1. The algorithm just works. Here we figure out which category our intersections were in. This is kind of opaque, so don't worry too much about the details here. The hexadecimal number is a lookup table, but what's important is, notice we are comparing the x component of each control point with the x component of our location. So the result depends on, for every point, whether it is to the right or to the left of the point we are rendering. Finally, the result of this lookup table tells us, for each intersection, whether it goes to the left or to the right, and we change the result accordingly, and finally return it. Then here is the boring loop we started off with. We iterate over all the curves, we calculate the cumulative winding delta, and finally, if that total winding number is not 0, then we paint the result. And that's it. I know that this was probably not of practical value to any of you, and had nothing to do with D, except for like 2 token code examples. So here's a quick tip I discovered. I have no idea if this is useful to anybody, or if this is common knowledge already, but here you go. In D, you can declare variadic functions like this, just like give me a bunch of ints, whatever, but the caller doesn't have flexibility in how it passes those integers. It can't pass in an array, it can't pass in a mixture of arrays and bare numbers. That's sad. Instead, declare this function as a variadic template function, declare an array of results, iterate over the arguments, and append each one to the array, and then, do whatever work you were originally going to do. If you do this way, then the caller can pass in the integers however it wants, which is much nicer. That's it. If you would like to check out the source code for this presentation so that you can watch it again without listening to my voice, you can get it from here. Please do not read the code because it is terrible, but there is a text file there with a list of links to other resources. So if you are interested, would like to learn more about this, do check that out. Thank you!